The lock-free object pool, again with the union free list of course. As I mentioned in my last video with the mutex object pool, the goal of this one is to test my hypothesis of the issue being either the mutex locking and unlocking overhead or the high thread contention focusing on one single point. And this is how I'm doing it. The structure of the pool template is basically the same again, with the constructor, the destructor, acquire and release methods, except this time I'm using lock-free atomic operations. And the issue was, although my CPU does support 128-bit compare and swap and 128-bit atomic operations, for some reason they aren't lock-free. I'm suspecting it's because of the C++ standard library implementation of the 128-bit atomic. That's my guess. So I opted for 64-bit packed pointers. And these are the packed pointer functions that I've defined within the template. The reason this kind of packed pointer and tagging is necessary is to address the infamous ABA problem that kind of originates from true sharing. What it is basically one thread looking at, let's say, object A. Then a second thread comes in, does some operations, converts, let's say, object A to object B, but then it converts it back to A, all before thread 1 has actually done something with object A. So from thread 1's perspective, nothing changed because it is still object A. But in reality, object A state changed from A to B and then back to A, which can cause a corruption of data, right? So to address this, we're essentially doing version control with our objects. That's what the tag is. There are better ways to address this true sharing and ABA problem issue. Ideally, you'd want to not have any contention at all. But if you need, sharing no matter what, then you could go for, I believe it's called epoch-based something, I keep forgetting. That method actually completely eliminates the root cause itself, and you never really get the ABA problem. This method is essentially delaying it as far as possible. So it's kind of a practical fix, not a mathematically optimal fix. Anyways, the pointer packing function is kind of efficient since we're using bitwise operations. We get the trick here is that when you get memory addresses, they aren't exactly 64 bits every time. They actually come in usually in 48 bits. And the top 16 bits, they're free space for this kind of application, for tagging and anything else. So what we can do is, when we get our memory addresses, we can add a tag to it, like a 16-bit tag, and every time acquire or release is called, we increment the tag. Now to do this, it's kind of simple. We're getting a 64-bit version of our address, and with a 48-bit, I guess, left shift, we're preparing a mask for that 64-bit address. But since we know that address is basically zeros on the first 16 bits, we can do p and pointer mask to get that, well, the main address itself. Then shifting our 16-bit tag by 48 bits, we have free space. That's how with the bitwise OR, we put all those bits into a tightly packed 64-bit value, which is our packed pointer. And what unpacking does is it just runs our packed pointer bitwise and with the mask. Since the pointer mask is 64 bits with zeros at the first 16 bits, it is essentially cutting off the tag part of our packed pointer and only getting the address. For tag unpacking, we do have to do a right shift to get only the 16 bits in the beginning. Now in the constructor, same way as before, we're using operator new and dividing that slab of memory into nodes. The only difference here is that we are packing it into a 64-bit integer and then storing it into our free head. Memory order relaxed basically tells the compiler that this is atomic. The acquire method, again, about the same. You get the current free head into an old head variable, an integer, right? Now this is where things get completely different compared to mutex, because we don't have locking. Each thread essentially spins. It keeps on trying until it's successful, right? This might sound inefficient, but compared to the risks that mutex carries of total deadlock and the tail end latency issues with locking and unlocking, you can afford to have like 50 or even 200 spins per thread at every single attempt, right? So while this loop runs, what we're essentially doing is we're getting the pointer and the tag, we're putting it in our new head value by incrementing the tag, and we're running a compare and swap check. What this does is compare exchange. I mean, it's comparing the free head to the old head, right? So in case we get free head.load into our old head and some other thread updates that free head, right, then this comparison would actually fail because free head has changed but old head is, well, it is in this thread's perspective exactly the same. In that case, it loads the new free head updated value into old head again and then tries again on the next iteration, right? But if the check passes, which means no other thread has touched the free head, then that's where the actual allocation then happens after the compare exchange check passes. So every thread could be updating the free head, interacting with it over and over, and this check would only pass between those gaps when no other thread has really updated the free head, and our thread, the current one that we are working with, it gets to update the old head to the current value and then finds that free head hasn't changed, if that makes sense. The release method, again simple, we destruct the object, reinterpret our node as a pointer value, then we're getting the current free head value and running the compare and swap loop again. Yeah, again it's the same kind of loop. We compare the free head to the old head, and if it passes, we move forward and we get our memory address sent back into the pool. If not, the old head gets updated and that thread keeps trying again. What I forgot to mention is there are multiple types of compare exchanges. Why we're using compare exchange weak is because it allows this loop to sometimes fail even if it passes. Now that is counterintuitive, but it actually makes everything more efficient. How do I explain this? With compare exchange strong, it's very rigid, right? But if compare exchange strong fails, you would have to explicitly define the logic to kind of rerun the loop again, right? By baking in that kind of failure logic within compare exchange weak, you don't have to really write all that again. Plus, I think there's something about deliberate failing sometimes that lets other threads, like other blocked threads, kind of gives them the chance to finish their job. Maybe that's how it gets an improved performance. I don't know, I'll have to look into this. So this is the result I found. I used the exact same benchmark as before, no difference at all. You can check out my previous video on the mutex version. So the single threaded new, delete and pool basically the same again, but the multi-threaded pool is still slow, which that basically tells me that mutex locking unlocking wasn't really the issue. Maybe there's a tiny improvement, like 2 seconds or so. The mutex one got like 10 seconds, but that's not really the bottleneck here. I think the main bottleneck is thread contention itself, because all 8 threads are operating on the same thing over and over. The CPU is still synchronizing those operations, and well, this is the result. That would mean there are, as far as I can come up with, there are 2 possible solutions to this. You could go for sharding, which is basically having multiple compare and swap lanes. So each thread isn't focused on one single point every single time. It can have multiple outlets, essentially. So it's multi-threading within multi-threading, sort of. That is a way to make this thing more efficient. But even then, I don't think it will ever touch new and delete levels of performance. The most optimal way to have reliable multi-threaded operations is to eliminate the need for contention itself. What do I mean by that? That means giving each thread its own little copy of the data you're using, its own memory and its own operations. So that is thread local architecture, right? That's what I think the Linux kernel uses, and it is the best possible way, since there is no contention, there's no false sharing, there's no true sharing. It's basically multiple single threads running together, right? I think that's what I'll do next, because sharding, although it can improve performance by a little bit, I think TLS is the way to go for the next experiment, right? That's what I'll try.